You know what bothers me? People think empty space is empty. I'm Richard Feynman, and I'm here to tell you something that'll make you question everything you think you know about nothing. Because nothing, the void, the vacuum, the empty space between stars isn't empty at all. It's actually the most violent, energetic, crazy place in the entire universe. And if you could somehow bottle up all the energy in just one coffee cup of empty space, you'd have enough power to boil every ocean on this planet. Sound impossible? Good. That means you're paying attention. Let me show you what's really going on. And I promise you, once you see it, reality never looks the same again. All right, let's start simple. I want you to do something for me. Hold out your hand. Go ahead, do it. Wave it around a little. Now, what did your hand just pass through? You'd say air, right? Oxygen molecules, nitrogen, some carbon dioxide. Fair enough. But between those molecules, what's there? Most people say nothing. Empty space, the absence of stuff. And look, I get it. That makes perfect sense. You remove all the matter, all the particles, all the energy, and you're left with nothing. Pure vacuum. Emptiness. That's what I was taught too. That's what every physicist believed for hundreds of years, and is completely, utterly, beautifully wrong. Now, I'm not trying to be difficult here. I'm not being contrarian for fun, though I do enjoy that sometimes. I'm telling you this because nature showed me something extraordinary, and it bugs me when people miss it. The universe doesn't care what makes intuitive sense to us. The universe does what it does, and our job is to figure out what that actually is, not what we want it to be. So let's figure it out together. Here's where things get interesting. There's this principle, maybe you've heard of it, called the Heisenberg uncertainty principle, named after Werner Heisenberg. Brilliant guy. Had some ideas I didn't always agree with, but this one's solid. Most people think the uncertainty principle is about measurement, like you can measure a particle's position and momentum at the same time with perfect accuracy. That's true, but it misses the really weird part. The uncertainty isn't just about what we can know. It's about what the universe itself knows. At the quantum level, things are fundamentally uncertain. Not because we're bad at measuring, not because our instruments aren't good enough, but because reality itself is fuzzy at the smallest scales. Now, here's where it gets fun. There's also an uncertainty relationship between energy and time. The shorter the time interval, the more uncertain the energy can be. And I mean really uncertain. For an incredibly brief moment, we're talking 10,021 seconds, a trillionth of a second energy can fluctuate wildly. The universe can borrow energy from nowhere, as long as it pays it back fast enough. So imagine you've got a box, a perfect box. You've removed every particle, every bit of radiation, every last molecule. You've cooled it to absolute zero. You've created the most perfect vacuum possible. According to classical physics, you're done. Zero energy, perfect emptiness. But quantum mechanics walks in and says, not so fast, buddy. Because of that uncertainty, energy is constantly fluctuating in your empty box, popping into existence, then disappearing, over and over and over again. These aren't measurement errors. These aren't things we just can't see. These are real fluctuations in the energy of empty space itself, and they change everything. Let me tell you what's actually happening in that empty box. Particle-antiparticle pairs are constantly being created out of literally nothing. An electron and a positron appear. They exist for maybe a billionth of a second. Then boom, they collide, annihilate each other, turn back into energy and disappear. Then it happens again and again. Billions upon billions of times every second. Photons flicker in and out. Quarks pop up and vanish before you can blink. The entire vacuum is seething with these temporary particles. We call them virtual particles, which is maybe a misleading name. Makes them sound fake, doesn't it? Like they're not real. But here's the thing, they're real enough to have measurable effects. Let me give you an example that I love. It's called the Casimir effect, named after Hendrik Casimir. You take two uncharged metal plates, put them incredibly close together in a vacuum, we're talking nanometers apart. And what happens? They attract each other. Now, why would two uncharged plates in a vacuum attract? There's nothing between them, right? Wrong. What's between them is the quantum foam, all these virtual particles popping in and out. But here's the clever part. Between the plates, only certain wavelengths of virtual particles can fit. It's like only certain notes can resonate in an organ pipe. Outside the plates, all wavelengths are popping in and out. So you've got more quantum activity outside than inside, and that creates a pressure difference. The vacuum outside literally pushes the plates together. Empty space is pushing on matter. Nothing is exerting a force. We've measured this. We can calculate it precisely. It's a real, honest-to-goodness effect that you can observe in a laboratory. And it proves that the vacuum isn't empty. It's full of this constantly fluctuating quantum foam. I used to describe it like the surface of the ocean. From far away, it looks smooth. But zoom in close enough and you see waves, ripples, bubbles, chaos everywhere. That's what empty space looks like at the quantum level. Never still, never calm, always buzzing with activity. Now, here's where I started to get really bothered. If virtual particles are constantly appearing and disappearing, that means the vacuum has energy. And not just a little bit, potentially a lot of it. So being physicists, we did what we always do. We tried to calculate exactly how much energy. We added up all the possible virtual particles that could exist at every possible energy level, at every possible wavelength, throughout all of space, and we got infinity, just straight up infinity, which is obviously nonsense. If the vacuum had infinite energy, the universe would have destroyed itself the instant it came into existence. So we went back and refined the calculation. We said, okay, let's be reasonable. Let's cut it off at the Planck scale, the smallest possible meaningful length in physics. We redid the math, being more conservative. The result? About 10 joules of energy per cubic centimeter of empty space. Now, let me put that in perspective. That's a 1 with 113 zeros after it, per cubic centimeter. A teaspoon of empty space would contain enough energy to power every star in the observable universe for billions of years. That coffee cup I mentioned, enough energy to vaporize the planet, maybe the solar system, possibly a good chunk of the galaxy. And I looked at that calculation and thought, well, something's obviously wrong here because we don't see that energy. Space isn't exploding. The universe is expanding, sure, but not from violent vacuum energy tearing everything apart. This became known as the vacuum catastrophe, or the cosmological constant problem. And you know what? We still haven't solved it. It's been decades, and we still have no idea why the theoretical prediction is off by 120 orders of magnitude from what we observe. That's not a small error. That's not even a big error. That's the worst prediction in the history of physics. And it drives me crazy because we know the vacuum has energy. We've measured it through the Casimir effect and other experiments. We know virtual particles are real, but we don't know why the universe doesn't rip itself apart. Maybe something's canceling out all that energy. Maybe our calculation is fundamentally flawed. Maybe we're missing something huge about how quantum mechanics and gravity work together. I don't know, and I hate not knowing. But here's what I do know. Empty space isn't a passive container. That's the real insight here. That's what changed everything for me. Before quantum mechanics, we thought space was like a stage. It's where the action happens, but it's not part of the action. It's just the background, the empty theater where matter and energy perform, but that's wrong. Space is an active participant. It's part of the play. It's dancing, breathing, interacting with everything in it. Every particle in the universe is constantly swimming through this quantum foam. Electrons aren't lonely little balls flying through empty void. They're being jostled, nudged, affected by virtual particles popping in and out around them. This is why quantum field theory became so important. We stopped thinking about particles as little balls. We started thinking about fields waves, ripples, excitations in something deeper. An electron isn't a thing. It's a ripple in the electron field. A photon isn't a particle. It's a wave in the electromagnetic field. And those fields, they're never zero. They're never turned off. They're always vibrating with quantum energy, even in empty space. You know those diagrams with the squiggly lines and loops that people associate with me? The Feynman diagrams? Those aren't just mathematical tricks. Those loops represent virtual particles. Every interaction between real particles involves these ghostly, temporary particles emerging from the vacuum, mediating the interaction, then disappearing back into the void. Every force you've ever felt, gravity pulling you down, electromagnetism letting you touch things, the strong force holding atoms together, all of it is mediated by virtual particles. You're not standing on solid ground. You're floating on a sea of quantum chaos. Every force holding you up is transmitted through particles that don't quite exist. Let me say that again because it's important. The forces that keep you from falling through the floor are mediated by virtual photons that pop out of the vacuum, transfer momentum, and disappear. The solidity of matter is an illusion created by quantum foam. Nothing is solid. Nothing is truly separate. Everything is connected to this seething ocean of virtual particles. And I find that beautiful. Let's think about what this means. First, it means there's no such thing as true emptiness. You can't create a perfect vacuum. You can't shield something from the quantum foam. Reality is interconnected at the deepest possible level. Second, it means energy conservation works differently than we thought. Energy can't be created or destroyed. That's still true on average. But at the quantum level, for brief moments, energy is borrowed and repaid constantly. The universe is running on credit, taking out tiny loans from the vacuum, paying them back before anyone notices. Third, and this is speculation, but interesting speculation. It might explain dark energy. You know how the universe is expanding, and not just expanding, but accelerating. Something is pushing space apart, and we don't know what. We call it dark energy because we're creative like that. Some of us think dark energy might be vacuum energy. This quantum foam we've been talking about might create a gentle outward pressure, pushing galaxies apart. Now, the math doesn't quite work yet. The vacuum energy calculation is way too high. We're off by that factor of 10^120. But maybe, just maybe, once we figure out why our calculation is wrong, we'll find that there's a small residual vacuum energy that's driving the expansion. That would mean the fate of the entire universe, whether it expands forever or eventually collapses, is determined by the properties of empty space, by nothing. I love that irony. The most important thing in the universe might be the thing we used to think was the least important, the void, the vacuum, the nothing that's actually everything. You know what I think is wonderful about all this? It's that nature surprised us. We thought we had it figured out. Empty space is empty, simple, obvious, case closed. And nature said, no, try again. That's what I love about physics. You can't force nature to fit your preconceptions. You have to actually look and see what's there. And what's there is always stranger, more subtle, more interesting than what you expected. Empty space isn't empty. Light doesn't travel the way you think. Time doesn't flow uniformly. Space isn't a fixed stage. Everything we thought was obvious turns out to be an approximation, a useful fiction, a story we tell ourselves because the truth is too weird. That chair you're sitting in, it's not solid. It's mostly empty space filled with quantum foam, held together by forces mediated by virtual particles. The air you're breathing, between the molecules, quantum chaos. Virtual particles blinking in and out. The light from your screen, it's not traveling through emptiness. It's a ripple in the electromagnetic field, propagating through a sea of quantum fluctuations. You're not surrounded by nothing. You're immersed in a cosmic storm of quantum activity. And somehow, impossibly, beautifully all, that chaos at the smallest scales averages out to create the stable, predictable world you experience every day. That's the real magic. Not that the quantum world is weird, but that something so chaotic creates something so orderly. Order from chaos, stability from fluctuation, the classical world emerging from quantum madness. I spent my whole life exploring that gap, the space between what we see and what's really there. And I found that the gap itself, the void, the vacuum, the nothing, was where the most interesting physics lived. Now, let me be honest with you about something. We don't understand this completely. Not even close. The vacuum catastrophe still unsolved. Why doesn't space have the insane amount of energy our calculations predict? No idea. How does vacuum energy relate to dark energy? Don't know. What happens to quantum foam near a black hole's event horizon or at the moment of the Big Bang? Your guess is as good as mine. And you know what? That's okay. I'd rather have questions that can't be answered than answers that can't be questioned. That's the whole point of science. Not to pretend we know everything, but to be honest about what we know, what we don't know, and what we're trying to figure out. Empty space isn't empty. That's not the end of the story. That's where the story gets interesting, because now we have new questions. What is the quantum foam made of? Is it fundamental, or does it emerge from something deeper? Why does the vacuum have the energy density it has, and not some other value? Could we ever harness vacuum energy? Probably not. Thermodynamics is pretty strict about that, but it's fun to think about. Does the vacuum play a role in quantum entanglement? In the emergence of space-time itself? Visual, interconnected questions appearing. I don't know the answers. Nobody does yet. But asking the questions, that's what makes physics exciting. So here's what I want you to remember. Nothing doesn't exist. The vacuum is alive with quantum fluctuations. Virtual particles appear and disappear billions of times per second. Space itself has energy, possibly enormous amounts of it. Empty space isn't a passive container. It's an active, dynamic, essential part of reality. And we're still figuring out what it all means. The next time you wave your hand through the air, remember, you're not moving through nothing. Visual hand-waving, quantum foam visualization overlaid. You're disturbing a quantum ocean. You're creating ripples and fields that extend across the entire universe. You're interacting with virtual particles that exist for less time than it takes light to cross an atom. You're swimming in the weirdest soup imaginable. You just can't see it. But I've seen it in the mathematics, in the experiments, in the beautiful, bizarre logic of quantum mechanics. And now you've seen it too. Nature's imagination is far greater than ours. The universe is under no obligation to make sense to you. But if you pay attention, if you really look, you'll find that reality is far more interesting than any story we could make up. Empty space isn't empty, and that's just the beginning of how strange things really are. Thanks for letting me share this with you. If you want to dive deeper into the weird world of quantum mechanics, stick around. Hit that subscribe button. There's so much more to explore. And drop a comment what surprised you most? The virtual particles? The vacuum energy catastrophe? The fact that solid matter is an illusion? The visual Feynman waving, archival footage. Keep asking questions. Keep being curious. Keep wondering about how things really work. Because that's what makes life interesting. And remember, if you think you understand quantum mechanics, you don't understand quantum mechanics. That includes me.